Fy, and then this with respect to r, that's just sine. Okay, so far so good. Partial z, partial theta. Very similar formula. And this is fx times the derivative with respect to theta here, we would get what? Minus r sine theta plus fy r cosine. And that's pretty much it. Now we move on to part B. It says we have to prove this thing. Now, since I already know these guys, I'd probably start from the right side and then try to work my way to the left. So I have partial z, partial r squared plus 1 over r squared times partial z, partial theta squared. That would be equal to what? What's this squared?
F sub x squared cosine squared theta plus 2 f sub x, f sub y, cosine theta sine theta plus f sub y squared sine squared theta.
Correct? Plus we have 1 over r squared times, now we square that term. So that would just be fx squared, r squared, sine squared theta. And it's a minus now.
Right.
2 fx fy cosine theta sine theta times the r squared, because we have r's attached to them, plus fy squared r squared cosine squared. Alright, now this 1 over r squared here is going to kill all the r squares inside here.
Right.
And so now we can start to regroup things. So I have fx squared times cosine squared theta. And here I have an fx squared plus sine squared theta, so I can factor that out. And this is 2 blah blah blah, minus 2 blah blah blah, so those guys just die right away. Similarly, I have fy squared sine squared theta plus the cosine squared theta. Of course, both of these are 1 as fx squared plus fy squared. Okay. Questions on that? Move on to 39. So this says z equals f of x minus y. Show okay, how do we do it? Well, this will sort of look like the chain rule.
The 13 rule?
What?
Can we use the 13 rule, like, you know, the partial of z of, with respect to x is equal to the partial of f negative fx FZ, that rule?
Oh, you mean the implicit differential? No, this is sort of explicit. Like you wouldn't need that. Is that how you thought of doing it? Like, I don't see why.
It occurred to me too, but I couldn't figure out how to make it work.
No. It'll look a lot more like how you did chain rule back in calc2.
Huh.
So sort of derivative of outside times derivative inside sort of thing. I mean, if you wanted it to look more like our formula in calc3, you'd actually have to do sort of like a substitution, something like u equals x minus y.
Okay.
And then you can say partial of z with respect to x is just partial of z with respect to u, partial of u with respect to x. Right? Or something like that, if you want to use that formulation, if you insist, but it's not completely necessary. So this would be that would just be partial z, partial u, and partial u with respect to x is just 1. Right, okay. So this is just partial of z with respect to u. And you can say partial of z with respect to y is equal to partial of z with respect to u, partial of u with respect to y. Or differentiate this with respect to y, you actually get minus 1. So this is minus partial z with respect to u, which means partial z with respect to x plus partial z with respect to y is equal to partial z with respect to u minus partial z with respect to u equals 0. Or you can sort of think of it as derivative of the outside times derivative of the inside. A similar thing would work.
So what is u? Oh, u is okay.
U is our inner variable.
Right.
So it's like here. It's like it's a chain rule before case 1 that we did, right?
Oh.
Where you have this guy defined in terms of a single variable, and that variable is defined in terms of 2 variables. Right? We never actually did that case.
Okay.
It's sort of the calc2 case, dressed up a little bit.
Okay. Thank you.
Other questions? First edition, second edition?
Second.
Okay, what's the question?
The temperature at a point xy is T of xy measured in degrees Celsius. A bug crawls to that position after 2 seconds is
Wait, T of x what did you say?
is temperature. T of xy is temperature.
Okay.
And then a bug crawls to that position after 2 seconds is given by x equals the square root of 1 plus t.
X equals square root of 1 plus t.
Y equals 2 plus 1/3 t.
2 plus
1/3 t.
1/3 t. Okay.
This temperature function satisfies Tx of 2,3 equals 4. Ty of 2,3 equals 3. How fast is the temperature rising on the bug's path after 3 seconds?
For 3 seconds, how fast is the temp rising?
Yeah.
Right, so this basically, they say basically what they want is the rate of change of t with respect to time when t equals 3, right? That's what they're asking for.
Right.
Okay. Now, notice that, when t equals 3, that gives us x equals 2 and y equals 3, right? So that actually gives us the point 2, 3, right? Which is what we had considered here. Now, partial of t with respect to t is just going to be partial of t with respect to x minus partial of x with respect to t. Well, it's a single variable function. We can put these here. This implies t equals 3. partial here at the point 2 comma 3 should equal to x of 2 comma 3 times the x dt at 3 plus ty at 2 comma 3 times dy dt. Now this we actually know, right? That's 4. Dx dt, I have to find the derivative of that with respect to t, which is going to be what? 1 over 2 radical 1 plus t, and I want to evaluate that when t equals 3. Plus this guy I know, that's 3. Derivative of this is just a third. So now here I plug in t equals 3, that gives me a radical of 4, which is 2. This is a quarter, and 4. So that's just this plus that equals 2. Yeah, so it's like after they give you these formulas, they actually give you the values at certain points. And then you just follow your nose with the formula, and then you start to plug in the points and realize that t equals 3 actually coincides with the points that you're given here. So you know that you can plug all these numbers into the same equation at the same time. And, that's how you. So the rate of change of temperature will be like 2 degrees Celsius or Fahrenheit, whatever units you're working in. Other questions? Yes, Kelsey? First edition, second edition? Huh? First edition or second? So this was in the second edition. Okay. Arctangent of x squared y. X plus?
X y squared.
We want to find what? Partial of y with respect to x. Oh, just dy dx? Yeah, it's the 2. Okay, ideas?
Just use everything on one side so it's equal to 0.
Right, we want to make it a level curve, so it's just like tangent inverse of x squared y minus x y squared equals 0. Call this guy f of xy, and at that point we know that the dy dx is just equal to minus x of x over x of y. So you take the partial of this with respect to x, what do you get?
You get 2xy over 1 plus x to the 4th y squared minus 1 minus x y squared.
And this is, all of this is negative. Yeah, and then f partial with respect to y.
X squared over 1 plus x to the 4th y squared minus x. Oh, so it's
That's good, so. Right. And to get this from, it's a complex fraction, we can multiply top and bottom by just denominator here. 1 plus x to the 4th y squared. And so that would look more like minus like that. Or this negative sign. Don't really think anything would simplify if I multiply those out, so I'd probably just leave it like that. One last question? Okay, so this is similar to the one we did before, where you're just going to use the chain rule formula and then you're going to plug in all the numbers. Right, because notice when t equals 3, your x is equal to h of 3, which is equal to 7, and your y is equal to x is equal to g of 3, which is 2. Y is equal to h of 3, which is 7 by this. Right. So it means you get the point xy is equal to 7, which is where they told you what the partials were at that point.
Right.
And so now we can say that dz dt, what's the formula for that?
Delta z, or partial z with respect to x times dx over dt plus partial z with respect to y times dy over dt.
Right, but this is just another way of saying f partial. And this, because your x is g, is just another way of saying g prime.
Right.
So this is fy, and that's this means that dz dt when t is equal to 3, you're just going to be given by fx at this point, 2, 7 times g prime of 3 plus fy at 2, 7 times h prime of 3. That's 6 times 5 plus minus 8 times minus 4. That's 30 plus 32. Equals 62. Yep. You don't have much time for that. Are you in the first edition or second edition? Okay, last one. Okay, how do we find partial z, partial s?
Partial of z with respect to r times partial of r with respect to s plus etc.
So partial of this respect to r is?
E to the r cosine theta. R with respect to s is just t. Respect to theta, negative e to the r sine theta.
Right, so this would be a minus.
Then that would be 2t over, it would just be t over square root s squared plus t
We're
squared.
doing with respect to s.
Oh, you're right, it would be s.
Yeah, that's it. There's not really much more you can do. E to the r t cosine theta minus s e to the r sine. Similarly, partial z with respect to t is partial z with respect to r. Partial r with respect to t plus partial z with respect to theta, partial theta with respect to t. And so that's e to the r cosine theta. Partial r with respect to t is just s, plus partial z with respect to theta minus e to the r sine theta times t. Okay, and that's it. Okay, so today what we're going to start in MATLAB, we'll obviously finish our homework at this point. It's not a lot of time left. So remember last time time before last time we talked about level curves, drawing the level curves. In the case where we have a two-dimensional surface projected onto the xy plane, they pretty much look like contour plots, so we are going to use contour plots to sort of think of level curves. And so that's what I want us to do. So one is to draw in MATLAB, obviously, contour plots. fix it. Moving on to 11.6. Okay, so in the interest of time, I'm going to write down some definitions and not derive them, but the derivations are in the textbook. They're actually not that bad. You're just playing around with vectors. But what a directional derivative is a derivative in a particular direction, right? So remember, we're in 3 space now, so there are an infinite number of directions that we can consider. And you might want to find the rate of change in any arbitrary direction, and so that's what a directional derivative helps us define. Now, it's defined in the following way. It's the directional derivative in the direction of a unit vector equals AB is denoted derivative of a function xy df. Technically, you're supposed to have xy here, but and find that's how we define the directional derivative. And notice here that we're allowing both x and y to change. That's why it gives us an arbitrary direction. So we're not only fixing the x to move, so we can only move in the x direction, or the y to move, so we only move in the y direction, but both we can allow to move simultaneously, right? So this can give us any arbitrary direction that we want, right? And it's given by some unit vector here. That's how we describe direction. We like describing direction as unit vectors, so that's how we're going to do it. There's a theorem that says that this guy, you can actually simplify. So you can basically prove from this formula that it's actually equivalent to this by the shorthand. You can actually do that. Again, not going to prove it. We're just going to use it. And there is one thing that you can see immediately from this formula is the following. Note. Suppose your unit vector is the vector I, right? That is the vector 1, 0, moving in the positive x direction. What would duf give you?
The vector of f(x) is 1.
It just gives you the partial with respect to x. And if u is j 0, 1, then duf gives you the partial with respect to y. That is our first partial derivatives are special cases partial derivatives are special cases of the general directional derivative. So this is the theory of a derivative in general, so to speak, in a particular direction. And if we happen to go in the x direction, we get the partial with respect to x. If we happen to choose to go in the y direction, meaning towards choosing the positive y as our direction that we're moving in, we get the partial with respect to y. So that's what they are. That's the definition. Pretty straightforward. So we don't use this very often, but you should definitely have this memorized. And there's another equivalent form that I'm going to tell you pretty soon you should have memorized. So let's actually do an example. Many different ways they can answer the question here. And you should make a note that this is the directional derivative at the point xy in the direction . In other words, the point where you're currently located, that's your xy, and that's where you're going to evaluate the partial derivative. The point you want to move towards, or the direction you want to move towards, those guys are the components that you plug in here. So then we're going to go through these examples. It should be pretty easy to catch on once you get into it. Okay, how do we do A? So you want the directional derivative at the point 1, comma 1, where u is the vector 1/2, comma radical 3 over 2. And you can check that that's actually a unit vector, right? So they gave you the unit vector. They don't always do this, but it's nice when they do. So what are we going to need? We're going to need the partials. So let's do that. Note that fx equals partial respect to x as well.
6x minus 2y.
6x minus 2y. So fx evaluated at the point 1, comma 1 is 4. What is fy?
2x.
Negative.
Negative.
Minus 2x. So fy at the point 1, comma 1 is just minus 2. Right? Here, your AB is just the vector 1/2 radical 3 over 2. Therefore, your directional derivative at the point 1, comma 1 in the direction 1/2 radical 3 over 2 is going to be equal to, let me just write it, fx at 1, comma 1 times 1/2 plus fy at 1, comma 1 times radical 3 over 2. That's 4 times 1/2, which is 2, plus minus 2 times this, minus radical 3. That's your answer. Right? Find the partials evaluated at your base point where you're currently located, and then multiply it by the components of the vector that gives you the direction you want to move in. Right? And here I did an example of 2-dimensional vectors. This actually can work if you're looking at a 3-variable function, 4-variable function. It generalizes in the natural way. B. Now we're at the 2.22 and want to move at in the direction where we're at an angle of pi over 6 from the positive x-axis. Okay, so find u f at 2, comma 2, where this time our direction is given by this. So this would mean u would be equal to what?
Well, same as last time, right?
Sine.
Cosine of pi over 6, sine pi over 6, because it's a unit circle, right? So the
That is correct, right? Because it's a unit vector, so it corresponds to a unit circle, and so you can describe any unit vector if you're given the angle by cosine sine, right? And so here we have cosine pi over 6. Here they're actually switched though, right? So this is radical 3 over 2, comma 1/2. And so here, f at 2, comma 2. Oh, well, we have to compute it for the new point. We did at 1, comma 1 last time. So now we know fx equals 6x minus 2y. This means fx at the point 2, comma 2 is 12 minus 4. Fy is minus 2x, so Fy at point 2, comma 2 is minus 4. This means our directional derivative is going to be 8 times radical 3 over 2 plus minus 4 times. This is 4 radical 3 minus 2. So, I mean, you could figure that out, but for those of you who like memorizing formulas, you could actually memorize the formula here in general. If U is a 2D unit vector determined by an theta plus Fy times sine. You can say that in general because it's on the unit circle. But you didn't really have to memorize that, but if you'd like, that's fine. C. Directional derivative, we're based at this point, so let's just start there. We know that fx is 6x minus 2y. So fx at 1, 2 is going to be 2. Fy is minus 2x. So Fy at 1, 2 is minus 4. How do I find my u?
You have 2 points.
Why is it minus 4?
It's 1, 2. Okay, that's an x. It's minus 2. Sorry.
Point A minus point B.
Right, so we're starting here, we're at this point, but we want to move in the direction of that point, so we really want the vector that moves from this coordinate to that coordinate. So it's final minus initial. But we want to make sure it's a unit vector, so we're also going to divide by its magnitude. All right? So u in this case would be final minus initial 3 minus 1, comma 4 minus 2. Then we divide by its magnitude. So this is actually going to be 2 squared plus 2 squared. So in this case, we will have 2, comma 2 over 2 radical 2. So just 1 over radical 2, 1 over radical 2. And then you apply the formula with that. Two times 1 over radical 2 minus 2 times 1 over radical 2. So in that case, the directional derivative is 0. In other words, the rate of change at this point, if you're moving towards that point, is 0. Right? Which means if you're actually looking on this surface, it would just be flat, like nothing really happened. D. Back at the point 1, comma 1. That gives us 4. How do I find my u here? Right. So this gave us a general direction, but you'll notice that it's not a unit vector. So you're going to have to take u to be v, divide by the magnitude of v.
Where'd you get 4 from?
9.
Huh?
Minus 4.
Algebra gets in every time.
Seeing if you guys are paying attention. And then at that point, it's 4 times 3 over 5 minus 4. Times 4. 12 plus 8. And that would be 4. Are we sort of getting the idea? We can write it in a much nicer way, which is where we're going now. Notice that def x, y. I mean, I get sloppy and leave off the coordinates every now and then, but as long as you understand what point we're evaluating at. It's fx a plus fy b. But notice that I could actually write that in the following way. I could actually express that as a dot product. Right? Now this guy here is a very important kind of vector. Very important. Especially for those of you going into physics. I know in the next course of this, 391, you're going to be using this vector all the time, and it's going to define conservative vector fields and all that, where you conserve work and energy and all that kind of good stuff. So these kind of vectors are pretty important. It even has a name. It is called the gradient vector. By this upside down triangle f, which I actually asked you in the quiz what that guy is. Right? And again, it generalizes to dimension. So if you know if f is just a function of x and y, then that means your gradient vector is just fx, fy. If f is a function of x, y, and z, then your gradient vector is fx, fy, fz. Right? It generalizes with dimension. Right? You just take the partial with respect to whatever coordinate you happen to be at, throw all these guys in a vector, and you've created what you call the gradient vector. Now with that notation, you can actually write the directional derivative in shorthand. This guy, dot product, u, which is a very nice font to write down. So this guy is just the vector of the partial derivatives of your function, and this guy is the direction you're moving. And again, it generalizes into 2, 3, 4 dimensions as necessary, very naturally. So we don't really want to talk about that. What else do I want to call? So this symbol is also called del, so you can call that del f, but I don't know anyone who calls it that. Well, let's see. An example. Here I'm given a function where I have to find the gradient vector, gradient vector field, if you want to call it that. So by definition, this is what vector?
F sub x, comma x sub y.
So what's the partial with respect to x?
2x plus 1z
Plus
ln of z.
Sine
sine
1.
one. We're doing part A,
Oh,
comma, partial with respect to y,
X squared.
okay.
Cosine
good. Part B, here the gradient f is equal to, definition,
So,
you mean f sub x.
Alright, there are three variables there, so I know it's going to be a three-dimensional vector. For each variable, I'm going to differentiate with respect to the component I'm currently in. And so partial with respect to x, it's going to be 2xy plus ln z minus yz, comma, partial with respect to y is going to be x squared, and
Minus
the middle
xz.
term goes to 0, minus xz, comma, partial with respect to z,
X over that
x over z
minus x.
Minus xy.
minus xy.
What did you mean when you said redo D using?
D in the last example,
Oh.
right? So in the last example we did
3x squared minus.
so f is 3x squared minus 2xy plus 4. Find f at the point 1, 1 in the direction d equals 3, minus 4. And so here, u we found was equal to 3 over 5, comma minus 4 over 5. I just want to rewrite it in the language of this dot product. That's basically what I'm asking to do. And gradient f would be equal to, partial with respect to x is 6x minus 2y, comma partial with respect to y is minus 2x. So your gradient f evaluated at the point 1, 1 is just the point 4, minus 2. So duf is just the vector 4, minus 2 dot product with the vector 3/5 minus 4/5, and that gives me 4. Another example to show that things generalize nicely. Suppose your f is equal to x over y plus z. Find the directional derivative direction 1, 2, 3. Okay, try that. Okay, so here we want to find the directional derivative at this point in that direction. All we have to do is take the gradient vector and the unit vector and dot product. So let's start with the gradient vector. Gradient vector here is equal to fx, fy, fz. This is equal to, partial with respect to x is partial with respect to y. With respect to z. So now the gradient vector evaluated at the point 4, 1, 1.
Half.
This means here it's a half.
-1.
Negative what?
Negative 1.
Negative 1. Now your u is going to be that vector divided by its magnitude. So that's just 1 over radical 14, 2 over radical 14, 3 over radical 14. This means directional derivative at the point 4, 1, 1 is equal to a half minus 1 minus 1 dot product with 1 over radical 14, 0 over radical 14, 0 over radical 14. So that's just 1 over 2 radical 14s
Minus 2.
minus 2 over radical 14
Minus 3.
minus 3 over radical 14. That gives you what?
Minus 11 over 2.
Minus 11 over 2 radical 14. Is that minus 11? It's 9, because it's a positive 1, and that would be minus.
Oh.
Tell me another way to write a dot product. Magnitudes, right? Magnitude of this times the magnitude of that times the cosine of the angle between them. No, since cosine theta is between minus 1 and 1, this means that the maximum that DUF can be is going to be when this is 1, right? So that's actually going to be the magnitude of the gradient vector, right? And the minimum that this guy can be is going to be the negative. And this is when theta equals 0, u is in the same direction as this. Here happens when theta is equal to pi, u is in the opposite direction. Alright, so just by rewriting the dot product, we can actually tell the biggest and the smallest that this guy could be, and we can also tell what direction it will happen in. So if we're at some point and we want to figure out which direction has the maximum rate of change, right? Where do we have to move to obtain the maximum rate of change? It's always in the direction of the gradient vector. And what is the maximum rate of change? The magnitude of the gradient vector. Right? I told you this guy's pretty useful. Did I an example? Oh no, I actually wrote down the theorem. They ask you about this all the time, so it's nice to have it in a nice theorem.
What is that, the directional?
Directional derivative, DIR. Just show you. all of these you can have just by knowing that you can write the properties of a dot product. And number 4 is actually pretty important.
What is that up to directional? Like,
Derivative, that's what I asked.
DIR. This directional derivative. The directional derivative is 0 in any direction orthogonal to the gradient. Right? Because it's a dot product. If you use orthogonal to gradient f, it's 0. What? Another way to find tangent planes is with the gradient vector, we have a nice way to find tangent planes. And this is really the way that I usually remember how to find the tangent plane. And the formula I gave you before was just a special case of this formula. So suppose that's a surface. But I know that the gradient vector at a certain point on the surface is always orthogonal to the surface by the dot product formula. Then the gradient of big F equals partial of this with respect to x, partial of that with respect to y, partial of that with respect to z is orthogonal to the surface at the point x, y, z. This means the general formula for the normal vector, we can actually write it in terms of a gradient vector. You can take the normal vector to be equal to the gradient vector. Evaluate it at the point you're looking at. And that yields the following formula. I can actually write the tangent plane as fx times x minus x naught plus fy times y minus y naught plus fz times z minus z naught equals 0, where fx, fy, fz are evaluated at the point. I can tell you can write this fx at x0, y0, z0, fy, x0, y0, z0. I don't like writing that. So I write it short and it's easier to remember when you write like that. And just know that you evaluate these guys at whatever point you're looking at. This actually gives you the formula for a tangent plane to any level surface. Can anyone see why this is equivalent to the formula I gave you last time for a tangent plane? Suppose that's your function. This means you can take fx, y minus z equals 0, right? And take this to be your big F of x, y, z. This means that your gradient of f would be partial with respect to x, partial with respect to y, and then this would be minus 1. Which would mean tangent plane by that formula would be given by fx, x minus x0, plus fy, y minus y0, minus 1 times z minus z0 equals 0. But then you move this guy to the other side. And you get the whole familiar form. Right? So this guy's really like the general form.
Okay, so this works for.
So this works all the time, right? This is why I like this way, right? Just whatever surface you're looking at, bring everything to one side, find the gradient vector, that's your normal, plug in the point, and you're done, right? So, and again, each partial is evaluated at the point, right? You don't leave because that's a mistake that I saw in some of the quizzes I wanted to talk about because I was very upset about it. I'll talk about it next time. What?
No, nothing.
Wait, you say I should move faster?
No.
I can. Oh, jeez, you guys have it on video. Whatever. You just rewind and watch it over and over.
No one has the lungs to read it.
What, you nobody got time for that? Okay, here's an example. Find the equation of the I'm done. I had to rush. I had to make sure you guys had homework. I couldn't like have you guys going home and like, what do I do?
We could always watch the video again.
Yeah, but that means tomorrow we'd have 2 homeworks. And you like seeing us suffer. So.
What do you mean 2 homeworks? We just did 1 section today.
Right, but if let's say we didn't finish today, and you finished tomorrow. And another section, then we'd have 2 homeworks now.
Yeah, I'm trying to spare you from that. Don't you see? It's tough love. That's what it is. Okay, quickly, tangent plane. Take this guy as your big F. So your normal vector the general formula for the normal vector is going to be that guy. So I'm going to take partial with respect to x, x squared y, comma, partial with respect to y, x cubed minus 2y, comma, partial with respect to z, 2z. So the normal at the point we care about, 1, 2, 3, that's just going to be, I plug in 1, 2, 3 for x, y, and z respectively. So that's 3 times 1 times 2, that's 6. This would be 1 minus 4 minus 3. This would be 6. This means tangent plane is 6 times x minus 1 minus 3 times y minus 2 plus 6 times z minus 3. I mean, I could simplify that a little bit. This tangent plane, right? And the gradient vector evaluated at the point, that's your normal vector, right? Which means that's the coefficient of x, y, and z. And then you take x minus x naught, y minus y naught, z minus z naught. And that's it, that's your tangent plane. So this is very good, especially when in the case where you have z defined implicitly, right? The previous formula we had works when z was explicit, z equals f of x, y. And all your x and y's are on one side neatly. Here, it doesn't matter if I mix the z up with everything, I can still get to the tangent plane with not much problem. And I didn't need to solve for z and worry about is it a plus or a minus square root, none of those considerations.
If it's ellipsoid and you need two of them.
Yeah, like you won't care, you won't need that consideration. There's no need to actually solve for z and worry about do I take the plus or the minus. Okay, let's see how much you guys remember about lines. What's the equation for the normal line?
Well, we need a point and a vector.
You need a point and a direction vector. What's the direction vector for the normal line?
Just the normal.
Right. For a normal line, your v is just equal to the n. Right, which here is 6 minus 3, 6, which is equivalent to 2 minus 1, 2.
And your
And
vector.
the point is also given.
1, 2, 3.
Point is 1, 2, 3. So the normal line, let's see who remembers the formula.
X, Y,
X
Z
equal to 1 plus 2t
equals 1, 2, 3. 1, 2, 3.
1, 2, 3.
Plus t times 6, 2 minus 1. 2.
Yep. Which you can write as 1 plus 2t, 2 minus t, 3 plus 2t. Right, and of course, you can do the parametric form or whatever. That's a normal line. Right? You know the difference between how that looks and how a plane looks. They're two very different things. Tangent plane here. What's my normal vector formula?
So fx, y, and z.
Which is
2x over 12,
x over 6,
y over 6,
y over 6,
c squared.
Z squared.
Oh, that should be a square. I said ellipsoids. I'm sure you pointed that out. Why is there 2 in the ellipsoid? So it's 2z over 3. So at 2, 2, 1, your n would be x is 2, so in the third, y is 2, that's also a third, z is 1, that's 2/3, which that's actually equivalent to 1, 1, 2. I can take anything parallel, the general direction is what matters here. And so this means tangent plane normal. So x minus 2 plus y minus 2 plus 2z minus 1. Because I took this to be my big f of x, y, z. That's it. Knowing about the gradient vector makes it easy to find the tangent. Just tangent plane. Just bring everything to one side, take the gradient vector. That's your normal. And we'll end there. So we've completed this section. Homework for this is due tomorrow. MATLAB homework is due on Wednesday.